I'm a sedimentary geologist. And what that means is I study sediments primarily, and I do it from a variety of perspectives. But I have two main questions in mind when I look at the sediments. One is the sediments are kind of like history, pages of a history book. And so I peer through them to understand Earth history. What happened in the past? What were the environments like? And I do it on timescales ranging from 600 million years ago to as recent as a few thousand years ago here in Lake Erie. I also look at sediments as vessels that contain and transport and react with fluids. When I do that, implications are for oil and gas, but also for looking at them in terms of, I look at them for the past 10 years or so, what happens if we take CO2 from power plants and instead of letting it going into the atmosphere, do something with it, prevent it from going into it, put it in a different reservoir. In this case, inject it deep into the earth. What would happen to the CO2 down there? Is that a means to limit the buildup of greenhouse gases in the atmosphere if we can't manage to do it in other ways? Or is that a component of our solutions? So those are the two kinds of questions that I address, and we could have a whole discussion about how they're linked, because they are. But we're not going to talk about that today. Instead, we're going to talk about the forces that shape our world. How is everybody doing in terms of hearing me? Is that okay? Okay. So Jim finished off last week with a brief introduction to plate tectonics, and I'm going to start there today, talking about Wegener's idea of continental drift proposed in the early part of the 20th century. And he saw a lot of evidence on the continents, primarily the southern hemisphere continents, that at one time in the past, he thought 200 million years ago, the continents were probably together and have since drifted apart. And the evidence he found were particular fossils that you find across the continents, but they line up where you find them. Particular types of rock structures, which if you put the continents back together, the rock structures line up again. And interesting aspects, climate evidence. He found evidence for glaciers, but not at high latitudes, in continents that are now low latitudes, and so should be warm and would be surprising to have them. As well, finding warm evidence for warm plants, ferns that might create coals and swampy warm that are now in Antarctica being found, the fossils of them there. And all of this fossil evidence he found, and also just the fit of the continents, he thought was strong suggestion that the continents had to be together in the past. And he believed it and argued it forcefully. And most people, a lot of people, particularly in the northern hemisphere, where the evidence was not as well preserved, did not believe him. And it set up a long, decades struggle with them saying, we can't do this, we can't even, let's stop talking about this idea because it's crazy, because it's not physical, we don't know how to make it happen. And that was the biggest problem with Wegener's idea. There was no way, no mechanism. Well, he died in 1930, but as people went along, they started getting some more data. So one set of data they found was paleomagnetic data from the continents, okay? And it's pointing to where the pole was, and if the continents are static and they're not moving, they should always point to the north, right? But they didn't. And in fact, Europe and North America pointed in different directions. And this slide is just showing the way that North Pole migrated, where it was pointing to until now. In the modern day, it's pointing towards the north. So the paleomagnetists working on the continents began to think, well, maybe there's something to this idea of continents moving. They also, as part of World War II, began mapping the seafloor. They were worried about finding submarines. They found a lot more when they were doing it. They found that there were large mountain ridges in the middle of the oceans, particularly in the middle of the Atlantic, long ridges, mountains, high mountains. And also, on the other sides of the continents, there were deep, deep trenches, okay? So they knew there was something going on with this topography. They thought the seafloor would be flat, and it wasn't. And so early in the 1960s, Hess and Dix linked these long ridges and suggested a mechanism of sorts, which is that there might be magma upwelling through those ridges, and that would cause the seafloor to spread apart. And Dietz called this idea seafloor spreading. And that idea of seafloor spreading then sent people thinking along the ideas of, well, if the continents are spreading apart, well, maybe we have an expanding Earth going on. And there was a lot of sort of thinking they had to go to make sense of that as well. Well, scientists had also been mapping using ships from the surface they could get at, noticing there were magnetic stripes on the seafloor with poles pointing one direction and then the next direction and forward and back. And in the 1963, Vine, Matthews, and then separately Morley submitted papers to Nature. Morley's was rejected, and then Vine and Matthews was later accepted, but they all now get credit for this. And what their papers said is they made a connection between these stripes and the magma welling up, and the recognition that people have been doing from looking at sediments that I do, right, and seeing that as you go through a sedimentary rock, and you get older and older and older, the poles that you measure on the sediments reverse. So you go through 100 years and it's this way, now 10,000 years it's going the other way, a million years it's going the other way. So that was evidence from the sediments that the magnetic pole was reversing over time from the northern hemisphere to the southern hemisphere to the northern hemisphere, pointing north and south. And so Vine, Matthews, and Morley put that all together and postulated that the magnetic poles reversing would be recorded by seafloor spreading as these magnetic stripes, and that those stripes would be symmetrical across the spreading ridges, along the spreading ridges. So now they're beginning to put it together, and the work continues. The ocean drilling program began to drill the ocean floors to see what's down there, and they found that the ocean floor, as they predicted, was basalt, an iron-rich rock, and very different from what makes up the continents, which is a less dense iron-poor rock, granite, and that the ridges, as you would expect if you were creating new floor here, were young at the ridge, 0 million years, and they got to as much as 180 million years in some places, and that was the oldest. But those are very young compared to the oldest rocks on the continents, 3.5 billion years old. And so something had to be making the ocean floor that you're creating go away. And they actually already knew the answer to this, so it was pretty easy to put the pieces of the puzzle together, because back in the 20s they had noticed these areas of trenches and subduction zones, and they had even seen earthquakes and mapped slabs going down into the mantle by where the earthquakes were being generated from. And so they really did have finally all the pieces and could put together the story of plate tectonics that we understand now, the model. And just before we get to the model, one more point. They also, with ocean drilling, met the thickness of the sediments. And it's 0 at the ridges because it hasn't been there very long. The seafloor is new. There's not a lot of time to accumulate sediment on top. And thick here on the edges of the continents, particularly on the sides of the Atlantic margin. If you notice on these other sides where the convergence is going on, where they were noticing a lot of earthquakes, there isn't very old sediment, none of the red, and it's not thick. And that's because that old sediment, that thick stuff, has been taken down and thrust up onto the continents by the subduction zones, by the convergence that's going on. So all the pieces of the puzzle fit together to create this model for plate tectonics, which is that we have spreading ridges where new floor is being created, transform faults where the spreading ridges are offset from each other, and there, instead of moving apart, the plates slide along against each other, and then subduction zones where one plate dives beneath the other. And water, and that causes melting and volcanoes. And also there's hot spots, which come from deep, deep, deep in the lower mantle, the core mantle boundary perhaps. And they're stable, but the plates move over them. So I'm just going to take you on a quick whirlwind tour of what we can see and explain by this in terms of morphology of the planet. First of all, we can understand hazards. Earthquakes and volcanoes are mostly along the Ring of Fire, the zone of subduction zones around the Pacific, and also along the ridges. So we can predict hazards and earthquakes and volcanoes using this model. But we can also go back and look at the Earth's surface and understand that. So Hawaii is a hot spot, and this is the trail of the hot spot as the Pacific plate moved across it, diving down into the Aleutian Trench in the subduction zone. So we can track the history of where that plate moved over the Hawaiian hotspot. Here is Iceland. It's a mid-ocean ridge on land instead of in the ocean, and it's on land because there's a hotspot that comes up right through the middle of that of the ridge. And so that's hotspot trace of volcano instead is on this side and also goes on the other side of the Atlantic. And the North American plate and the Eurasian plate are moving apart. The famous San Andreas Fault we can understand. Now it's a transform fault, not on the ocean, but we can see it luckily on, not for people who deal with earthquakes, but on land so we can see what it is. So here, the western part of California and Baja, Mexico are moving northwest relative to the rest of the North American plate. And you've got the Andes Mountains in South America. This is a subduction zone. Here you have the Pacific plate diving underneath the South American plate. And that process, and Darren works there, who's in this audience and does, so these are sediments that were deposited in shallow marine, terrestrial marine environments that have been thrust up by those convergent processes. They're no longer on the seafloor. That's why we didn't see them on the western side of the continents. They've been thrust up on top of each other and folded and tilted, so you can see layers of sediments. Those were deposited, those layers horizontally, and now they've been tilted and thrust up over, forming mountain belts. And finally, here is Mount St. Helens. So the Cascades are also a subduction zone. And as Jim told you about, you subduct water, it lowers the melting temperature, and so we end up with melting and magmas generated and volcanoes.
Perhaps a bit off topic. I asked this last week and didn't understand the answer. And I understand that the upper layer of sediment will be younger than the lower layer of sediment, but how are you establishing the 600 million year date? How are you dating this stuff?
So Jim is going to give a whole talk on dating in the last section. We set aside that would be an important thing. But the primary way that we do it today, and that they were doing back when they were figuring this out. So they had just discovered radioactivity, okay, back at the time of Wegener and all of that. And they were just beginning to use that to figure out how old the Earth is. And what happens is minerals that are erupted from volcanoes, okay, have a radioactive element in them. So zircon, which is one that we use, has uranium in it, okay? Other minerals that I work on with dating have potassium in them. They both have radioactive isotopes. Those minerals and their isotopes are locked into the mineral when it's erupted. So it melts, it's flush, it's in equilibrium with whatever, and then it erupts, it cools, it's quenched, and those minerals, the isotopes are locked in. And the uranium decays to lead, and the potassium decays to argon. And by knowing how much parent there was, and how many daughters there are, and how long it takes for each generation of daughter to be created, you can go back and calculate how old they are. It's more sophisticated and complicated than that because there's a lot of work that's done to make sure you know how many parents there were, right? And especially with uranium lead, there's a lot of backup systems that test each other against so that you have multiple lines of evidence so you can know when you're off. But that's the basics of it. When you get younger than you can do with potassium argon, people do the dating with carbon. And there's radioactive isotopes of carbon.
When you have an eruption like Mount St. Helens, what causes the eruption itself? I mean, do the tectonic plates? We never thought that in geology 60 years ago, and I get kind of confused about whether the tectonic plates ever change in some way or another, and you get a big eruption.
That is a question beyond my expertise level. I would say that I don't think the immediate cause of an eruption is something going on in the plates themselves, or even an earthquake, something like that. I don't think so. It's possible that in some circumstances it could be, but mostly I think the eruption is internal magma dynamics. So the magma chamber builds up with enough volatiles and pressure and magma that it eventually just blows its top, and that's what it is. And it's just how long it takes for that to happen. Yeah. So now I'm going to talk about some more things that we can look at and understand using the plate tectonic model. So we can look at the surface of the Earth and understand the topography on the surface. We can understand hazards. We can understand volcanoes. We can also understand resources. Okay, use that plate tectonic model to better understand that. So porphyry metal deposits. Porphyry, I just looked this up with Patricia yesterday. She said, what does porphyry mean? It means purple. It means purple. It was a purple gem, purple cloth in Greek, okay? And it has now been co-opted by the geosciences to talk about colorful, including green, it doesn't have to be just purple, but colorful metal deposits that we see in rocks. So, and they are all these colorful ones, which can be gold and copper. A lot of them are generated, the predominant mechanism is by hot fluids. And where do you get hot fluids? Volcanoes, okay? Percolating through the earth, and those hot fluids leach out the metals, which are distributed and not very concentrated, leach them out, concentrate them, cool down, and deposit them out, okay, in a concentrated area. So since metal deposits, precious metals, are associated with volcanoes, one might expect there to be a geographic distribution of them, which there is. Here we look at the porphyry ones are the red, and the other ones that have been shed off them and deposited in sediments, and they're all along the subduction zones, okay, where plates are diving around each other, and on the other side the subduction zone, and also in this middle part where the African plate and the Asian plate and European plate are colliding and crushing into each other, and the Himalaya are being created, built up, okay, all of this area. So they're in places where there are now active volcanoes, or there were lots of big active volcanoes and still are in the past. But they're mostly young mountains, young volcanoes. And I'm using a geological term for young, which in this case, I mean, 100 million years and younger, okay? So, and they're young because these are processes that are actually happening pretty shallow in the earth. And so, and they're high in the mountains, and you have something that's high in the mountains and not very, very deeply, and it's eroding because that's what mountains do, then over time, those copper deposits get eroded off and out and deposited. So we don't keep them for a very long time, and that's why they're young, okay, in that geological sense of the word for young, which for now, I'm going to call young. I said 100 million years. Well, in this case, young is going to be anything since the breakup of Pangaea. Okay? So Wegener thought there was this supercontinent. He called Pangaea or all lands. And with his idea of continental drift, okay, which later became seafloor spreading, that supercontinent broke up beginning about 200 million years ago, broke up, and the oceans spread apart, created the Atlantic Ocean. And much of what we see in the modern day, in terms of mountains where they are, is explained by this breakup of Pangaea. So that has shaped the surface of the Earth, okay, including where these metal deposits are. I'm going to take you back now, before Pangaea, to understand some other things. So we can look at this to try to understand the topography of the United States. all of this topography over here in the western, if you look at it, it's pretty sharp. You know, those are where the big mountains are, right? I like to tell my students that the alluvial fans in Death Valley, okay, I take them there in the spring. This is the sediment that's shed off the mountains and accumulates at the bottom in the valley, okay? And they have 5,000 feet of relief on them. So if you started at the bottom when you walked up to the top, you have to walk 5,000 feet. There's more relief on the detritus at the bottom of the mountains in Death Valley than there is in all the Appalachian Mountains, okay? So these are big relief, big structures. They're young. All of this has been formed since the breakup of Pangaea. Some of the sediments and rocks are old, but all the topography, all the landforms are young. This flat, so based on that, this flat inner part of the state country, what do you think? Is it old or young? It's old, that's right. It's the stable core, and it has not seen tectonic activity for 1 billion years and more, okay? It's old. Now, it's not old rocks right there. The old rocks are buried under thousands of feet of sediment that were deposited in seas, and there's beautiful fossils that you find there. They're deposited in seas, okay, that covered this area once upon a time, all right, during times of high sea level, and so in the Ordovician, the Cretaceous. And then we have the Appalachian Mountains. And they're not as sharp as this stuff. They look kind of muted and worn down, and they are. So we're going to talk about the Appalachian Mountains and how they formed. And then you have this area here, which is also flat. That's the coastal plain, and that is the remnant of this breaking apart of Pangaea. So that's a very young feature. And it's those sediments that were shed off the mountain and accumulated where the sediments were thick on that map of sediment thicknesses. Okay, so to understand the Appalachian Mountains, we have to go back before Pangaea, and we have to look at how Pangaea was formed and created, okay? And we start with Laurentia, this stable core. This is what's underneath, okay, the middle part of the United States, okay? This underneath Ohio, okay? This ancient continent this Laurentia was formed 1 billion years ago from this Rodinia, part of another supercontinent, okay? And then we have a bunch of little microcontinents. You've got the tectonic highlands, which would be something like Japan today, crashing into Laurentia. We have Baltica, so Eastern Europe. And we have Avalon, which is a bit of England, okay? So these are these continents where they are now, but what they were back then, okay? And the Iapetus Ocean. And each of these is crashing, converging plate tectonic subduction, okay, converging in, building mountains, creating volcanoes, the stuff that we've learned about from the model of plate tectonics, but happening 400 million years ago, okay, before Pangaea. So we have to look at that. And here's a picture of what happened. This is Laurentia, so this is the eastern coast of North America. This is Ohio, okay? Here's that tectonic highland, Japan-like structure. Here's Avalon, England. There's a ridge there, but it's going to close. And here's the subduction zone diving underneath. It's crashing in, causing all sorts of thrust faults that build up, okay? And then sediments, this gray stuff at the top are sediments that are being shed off that mountain. So I'm going to draw your attention here to the sediments, because that's what's preserved. That's what we can look at when we go back in time, are the sediments. The mountains get worn down. Also, that's because that's what I study. You can go find the volcanic arc too, actually, and study that if you want. But so here we have this, before the collision occurs, we have this wedge of sediments. Yellow is sand, and the light blue are limestones. It was actually kind of like the Bahamas. It was warm, it was tropical, it was an ancient Bahamas, beautiful seafloor, okay? With reefs and all the stuff that you would find there, building up. And then shallow water. And then along comes this sin, and the weight of this mountain weighs down the crust and creates a basin. Basins are what we talk about sediments. It's where the sediments go in, they fill in the hole, and they accumulate, and that's why we get to study them, because they're preserved in the basin rather than being eroded off the highs. Okay? So that happened. And then after it finished with the tectonic orogeny means mountain building, it happened again. with the Acadian, where Avalonia oppression, and then it happened again. So this is the history of the Appalachian Mountains. So I just want to take you back, though, and let's look. So here's what we call a passive margin. It's North America today. There's no tectonism going on. You've just got, Ohio, and it's quiet, and it's smooth, and here's the great Bahama Bank, okay, floating up there, and it's a beautiful tropical sea that's very quiet and calm and oxygenated and full of life. And then here comes the tectonic highlands, and what it does is it weighs down the crust and causes some faulting to go on, and it creates a bit of an isolated basin there that's not open to the sea, that's not having a lot of circulation and waves and everything. And into that, and that's deeper, and into that, in the deepest part of it, it's very quiet and deep and low oxygen. We don't have good circulation coming in to oxygenate the bottom. And so now there's no animals living at the bottom of this sea, all right? And there's not a lot of big coarse sand. Instead, it's very fine shale, clay, and organic matter. The algae that are floating in the surface water, photosynthesizing, okay? They die and they percolate down and they fall and they accumulate here and they make what we call black shales after they get buried, okay? So no life, no oxygen, just a lot of accumulating sea slime in the bottom of this mountain, of this basin. All right, and then we fill it, the mountain gets bigger, it erodes off, and we overlay it with sandstones, okay, that are shed off that mountain. That's what underlies Ohio, okay? And that cycle is repeated. Shale going up into sandstone, shale going up into sandstone, a couple of times with each of these mountain building events as these continents collided. So when we look back, here's we're starting at the top one, the Grenville orogeny of a billion years. This is how we formed Laurentia, the core, the stable core. And then it broke apart, all right, about 500 million years ago. And now, here we have the middle part. We've got the tectonic Avalonia coming in and crashing in and creating these basins with shale at the bottom and sandstone, shale at the bottom and sandstone. And then here comes Africa, okay? This is the final assembly of Pangaea. Africa is now coming in. And then the final part, here's Africa colliding, okay? And it makes the Appalachian Mountains. Except they weren't the Appalachian Mountains, they were like Tibet. They were giant, okay? And then Pangaea breaks up, rifts apart, and here's the modern day. All this stuff is buried underneath the coastal plain. Here's the Atlantic Ocean, and here's what's left of the Appalachian Mountains, of that giant mountain range that formed, that was like the Himalaya. And here's what it is like today. This is looking at the Appalachian Mountains. It's an air photo from, from above, and you've driven over it, I'm sure, and you go up and down, right? And these squiggly lines are folds of rock. If you looked at these lines in cross-section, you would see a fold folding up and over. That we call that an anticline when it goes up, and synclines when they go down. So these are just a lot of folds from where these rocks have crumpled together. Now notice that the stream goes right across them. That's what we call a cross-cutting relationship, and it tells us relative ages. And what that's telling us is that this stream is younger than these mountains. It's not younger than the folds, but when the stream formed, the topography was flat, and it eroded down through it. And so the stream stayed there even as the mountains rose up because these more resistant layers didn't get weathered or eroded away, okay? The topography was buried, but underneath flat sediments, okay? So the stream was there and it could just cut down through it. And we know that actually above these, we do studies from looking at the sediments, there's probably about a mile of rock above them in the past, okay? Now we're going to go underneath the Appalachian Mountains, and this is a cross-section from Ohio to West Virginia. And what we're seeing is the Appalachian Mountains, okay? And these layers of sediment that underneath Ohio are lying flatly, okay? And these show different layers of carbonate shale sand, this pattern that I talked about. This is a map of Ohio, and it's showing where people have drilled for oil and gas, okay? And they're drilling in shallow sandstones. But the oil and gas that is in those shallow sandstones originally came from what's indicated by this, the Utica shale. You guys may have heard about fracking, and okay? All of that, well, they're now going down into the Utica shale, which underlies all of this and is the source of the oil. When the Appalachian Mountains were buried, it buried this formation deep enough to take the organic matter that was accumulated in those basins from the photosynthesizing algae in the surface waters and didn't decay and go away because there was no oxygen. It took that and turned it into oil and then into gas, okay? And so this is the peak area of where the oil and gas has been generated, and it migrated up from there, and it's where they have been getting oil and gas out of the shallow sands just of the Clinton. And so now, because a lot of that oil is gone and gas is gone, and because 10 years ago the price of natural gas went up a lot and it became economically possible and technologically possible, where people are drilling below those sands down into the shales, into those source rocks, instead of the reservoirs, and turning the well horizontally and fracturing them and getting the natural gas out. So now we're explaining it. So all of this fracking can be related to plate tectonics as well.
Do you think a lot of that hydrocarbon and gas and coal and oil was lost in the movement of the plates over millions of years?
Yes, a lot. So a lot of it, so much of what was originally there in the Utica, has migrated out of the Utica into these shallower sands, but a lot of it migrated out of those shallower sands as well into even shallower formations, and for the gas escape to the atmosphere. In fact, that's, the oldest oil wells are in Pennsylvania, the first one in Pennsylvania, early ones in Ohio, and it's not that they were, brilliant. They saw oil seeping out of the ground. And they went and drilled there, where the oil was seeping out of the ground, okay? So, and that's what happened. So yes, a lot of the oil has already come out. And when people talk about fracking, contaminating aquifers, one of the problems that we have is that there really are natural accumulations of natural gas in people's aquifers that are coming from these deep formations, and it percolates up over millions and hundreds of millions of years naturally, and it can be hard to tell what's been caused by oil drilling and hydraulic fracturing and what was there originally if you haven't already done a lot of background data to understand what's in your well.
In your earlier map of the flat Midwest, holding that thought, and then the fracking and the digging down, can that in any way upset or lead to more tectonic movement?
It can, because there are faults down there underneath, deep in that basement, deep underneath all these layers of flat-laying sediments that accumulate in the oceans. There's what we call basement rock that has been around for 1 billion years from that formation of Rodinia. And that basement rock has a lot of faults in them, some of them mapped, others not. So there was an earthquake, a series of earthquakes in Youngstown that you all may have read about, and that was caused by injection of brine, not fracking, not to fracture the rocks, but to dispose of brines that are generated by oil and gas development, and also fracking fluids when they're contaminated. So, and that was caused by that because they injected into the basement, into those faults, and generated earthquakes. Now we have something like 180 injection wells in Ohio. That's the only one that has caused earthquakes. So we have to weigh risks, and there are consequences, and we have to weigh that. But yes, it can. And there are a lot of work being done to understand how big they might be and how often and how to avoid.
I'm hearing what's moving and where and when and all that. I haven't heard why, the driving force. Is the Earth trying to reach some state of equilibrium, and will it reach it? Or
for asking that question, because you're right. I didn't even mention that. And I should have a slide. So the driving force is convection in the mantle. Okay? So the mantle, and people debate, and I'm not sure where the debate is right now, whether the entire mantle convects or whether it divides into cells where the top half convects and the bottom half convects. But it's just like if you were put a pot of water on the stove and you heated it from the bottom and it's cooling off at the top and it starts to boil and bubble. Okay? Now make it not water, which is not very viscous, make it molasses, and it's not going to bubble up like crazy all over the place, and it's going to set up cells that are rising up and around like this, and it really is big cells going on where the slabs are diving down and the stuff is coming up. Now there's a debate, and I think they're moving back to it's actually the cold slabs that's driving it, perhaps more than heat from the bottom rising up, but that's one of the questions. All right, this is the 7th inning stretch, and I need 9 volunteers. So this is the timeline. Everything I've taught you about so far has happened in this part of the timeline when there is a lot of fossils. But Jim talked to you about stuff that goes way back to 4.5 million years ago. So this is one way to visualize it. We're going to do it another way. Chris, I need you first. Chris is going to represent the first 500 million years.
I knew I was.
He's going to stand like this, arms out. 500 million years. This is the Hadean. There's not much left of the Hadean. We don't see much rocks of it, but Jim showed a picture of a zircon. So there was plate tectonics, there was water, but that's all we have, a zircon, okay? Not much. Okay, come here. So now Tim is going to stand up, and I'm going to have a few more. So this is 500 million years, billion years, a million years, a billion years, 1.5 billion years, 2 billion years, 2.5 billion years, and we're going to stop there. Okay, this is the Archean. There's life, probably going back to 3.5. Okay, Archaea, simple single-celled animals. They don't even have a nucleus inside of them, all right? There's no oxygen, no free oxygen on this Earth, okay? And that's all we've got, all right? But there's really cool rocks called banded iron formations, which I'm going to tell you about. And now we get to a very interesting event. When the Earth begins to get oxygenated, we begin to have oxygen in the atmosphere. And so here we go. Where were we? 2.5 billion years? Okay, 3 billion years. 3.5 billion years. 4 billion years. Actually, I went backwards. So 4 point whatever. We're now 4 billion years into it. So this is only 500 million years ago. Okay? This is all the Proterozoic. Proterozoic is life. Proto is early. So there's single-celled organisms with nucleuses, and that's it. But some of them clearly are photosynthesizing and generating oxygen because we have oxygen in the atmosphere. Not a lot, but it's there. And then here, the star of the show, the last 500 million years. Here we have the Cambrian explosion. Everything I've talked about today is in here. All the fossils that you see, the dinosaurs, all of that is in here. When you hear about the Cretaceous and the extinction of the dinosaurs, that's like right here, like really at the end. And the evolution of humans, I work in Ethiopia on very early hominids. 3 million years ago, I don't know, I didn't do the math, but it's somewhere on the fingernail, okay? So that, and the last time when, some micron. So this is our history, our timeline, which I think it looks a little bit better than that. I'm now going to go back to Chris's time and work our way up with that through these time periods. Remember, Hadean, Archean, Proterozoic, and Phanerozoic. Phanerozoic means visible life. Okay, you guys can all sit down. Thank you very much. And what we know about that long stretch of time, as Jim told us, is that there was water. And there were continents and there was plate tectonics, but there was water during that whole time. Now water, as you know, boils and it freezes, and it doesn't have to go that far out from the temperatures that we see in our, to do that. And yet there was water. Somehow the Earth managed that. And it's even more complicated that it did that because the sun, back during the Archean, was 25% less strong, was giving out 25% less energy, okay, than it does today. Physicists do that. It's based on nucleosynthesis and their understanding of what's going on in the sun, okay? But it's called the faint young sun, and it wasn't as strong, okay? And yet there was water. And we have to think about that in terms of a greenhouse effect, okay? So the greenhouse effect, the sun's energy passes right through the atmosphere, okay? The rays of the sun. It might bounce off them if there's clouds. It'll reflect off. Or it might bounce off the surface if the surface is white. It's like walking on the pavement when you walk on the white. It's cool when you walk in the dark. My kids walk around barefoot all the time, and they're always screeching when they're walking dark, you know. All right, so it might bounce off the white, but it'll get absorbed by the dark parts of the Earth. When it absorbs, the Earth heats up. It re-radiates as heat, infrared radiation. Heat is infrared radiation. Infrared radiation has a longer wavelength than visible light and UV that's coming through from the sun, and so it gets absorbed by greenhouse gases in the atmosphere. Those greenhouse gases in the atmosphere warm up because they're absorbing the heat, and they re-radiate that heat outwards. Some of it goes to the atmosphere, some of it comes back and warms the Earth again. That feedback, that mechanism is the greenhouse effect. And it's critical. If we didn't have any greenhouse gases in our atmosphere, it would be negative 25 degrees, okay? The average temperature. We would not be very happy. Celsius, not Fahrenheit, but they're close at that point. Okay. This is just a picture showing these effects. This is how much of the sun is being reflected from the Earth. And you can see the oceans are dark. They're absorbing. The continents are light, especially the big desert areas, okay? They're reflecting. And then this is what's being re-radiated out, okay, as heat energy. And it's biggest and strongest around the equator because that's where it's hottest and the sun comes in the most directly. And then we have this part where there must be dust. Here where it's not radiating much, right? Because over here we have dust clouds or clouds that are reflecting it off, all right? Well, there's two explanations for the faint young sun that people are trying to figure out, and they've been debating for decades. Either the ancient Earth had more oceans and therefore absorbed more of the energy from the sun, right? And that's why it stayed warm, okay? So we had less reflection, and therefore the Earth was warm enough. Or we had more greenhouse gases. When they do the calculations, neither one of them is quite enough to do it, and yet I don't understand it. We still battle over it, which one could do it all, instead of just saying it's both, okay? But what it comes down, the reason why they're battling is we don't know how much each one was important, how significant each role was. But they both were playing a role. Well, we know these are limestones. These are organic rich shales, which are generating natural gas deposits. And this is West Texas, the only national park dedicated to geology, Guadalupe National Park. These limestones hold CO2. If all the carbon that were in the limestones on the world, okay, were in the atmosphere instead, it would be 100 times more than the weight of all the nitrogen, oxygen, and everything else that's in the atmosphere, not just the CO2, which is only a small fraction of our atmosphere, okay? It'd be like we were buried under a kilometer of ocean. The weight of the atmosphere above us would be a kilometer of water thick, okay? If it were not trapped and stored in sediments rather than in the atmosphere. So those limestones, carbonates, sediments, are an important mechanism for controlling greenhouse gases. And over time, somehow, as the continents were built, and we don't know how fast this happened, CO2 and carbon that was building in the atmosphere was taken out of it and stored in these sediments. And if that didn't happen, we'd be Venus. So let's go back and look at what's going on. We've got very simplified volcanic rocks that are made out of calcium, and silicate. This is basic, it's much more complicated than that, but basically you can think of this as this is the continental crust, calcium, silica, and water. It weathers because there's CO2 in the atmosphere coming out of volcanoes, and they make the rocks acidic, and the acidic breaks the rocks down and releases the ions. So calcium ions go on, silica ions go in, and carbonate ions go dissolve into the rivers and travel in the rivers into the oceans. And this process is what makes the ocean salty. Okay? Well, once we have these in the oceans, actually, the calcium and the carbonate build up, and they become super saturated with respect, if you get enough, with respect to calcium carbonate. Now it's possible for critters to take calcium carbonate out of the ocean and create shells. And it's possible for just abiologically, without animals, to just precipitate this stuff. So we form carbonate. And it settles down and lands on the crust. Okay, and we have these limestone sediments. There's a cycle that happens. It gets subducted in the lithosphere, melts, erupts, and it takes the carbonate, turns it into rock again, and then takes that carbonate rock and turns it back into silica and has the whole process going on, okay? So there's a cycle by which CO2 is cycled between the continents, the atmosphere, the ocean, and the crust. And with this cycle, if we go faster, if there's more CO2, okay? Because if there's more CO2, it gets warmer, chemical reactions happen faster, all right? So reactions happen faster, there's more weathering, you get more CO2 here, that kicks it out. It's called a negative feedback. If it gets warm, then these reactions will trap the CO2 in the sediment. If it gets cold, those reactions that trap the CO2 in the sediment slow down, and more of this CO2 coming out of the volcanoes builds up in the atmosphere. And so it's maintaining an equilibrium. And it looks like it's been able to maintain that equilibrium over the whole Phanerozoic. There have been times when there have been ice ages and not, but we've come out of them. We've always come out of them. So these are times when there have been ice ages, and this is what we think CO2 would be. And during the ice ages when they're high, the CO2 is low. But you know what? It hasn't gone too crazy. We've always come back, all right? And even at the very beginning of the Proterozoic, the end of the Proterozoic, the ice ages may have covered the entire Earth. It's called the snowball Earth. At least there was ice at the equators at sea level. And even with all that reflection from the ice everywhere, it was able to come back. The Earth was able to return because CO2 kept coming out of those volcanoes. The greenhouse effect built up, and it eventually warmed the Earth again to bring us back to water, okay, and melt the ice. In the Archean, if we go back, it's not just calcium, but there's also going to be free iron. And that's because there's no oxygen to take that iron out. Instead, there's all these early life that use hydrogen sulfide and all sorts of crazy things. But we do know that there were things that were making oxygen, cyanobacteria. This is slime from the modern, but they've been around for billions of years. But it wasn't building up in the atmosphere, and it should. But there's enough stuff taking it out, and reactions with methane will take it out. Reactions with hydrogen sulfide will take it out. So there wasn't enough of it yet. We don't really understand what caused there not to be oxygen building up and what caused it to build up. We know that about 2.5 billion years ago, it did begin to build. These are just fossil evidence that 3.5 billion years ago, 2 billion years ago, there was these cyanobacteria that were generating oxygen for the atmosphere, but it wasn't going in. And how do we know it wasn't going in? We know there wasn't oxygen building up in the atmosphere in the Archean because we have these banded iron formations. If there was oxygen in the atmosphere, any iron that's weathering out of the crust would get oxidized. An oxidized iron doesn't travel. It just stays right where it is. If you go to your soils, they're red. That's because there's iron trapped in the soils, okay? In iron minerals in the soils. It doesn't go into the water and travel down the streams to the ocean. But in the Archean, we have these iron sediments that tell us that it got off the continents, far out into the oceans, but it didn't stay dissolved. Eventually, we got to little pods of life, okay? Little pods of oxygen, and then it precipitated out. So we know there was oxygen some places in the early life, but there wasn't enough of it to have oxygen built up everywhere in the atmosphere. Now this banded iron formation is a pretty nice one, because in the middle you see this rock here that's weighing it down. That's a drop stone from a glacier, okay? So there's a volume of ice above that has rocks in it, it drops it down, it weighs it on the rock. And this one is coming not in the Archean, not more than 2.5 billion years ago, but 600 million years ago. So most of them were old, right, until about 2.4 billion, and then we don't see them anymore. And that means oxygen rose up in the atmosphere enough to stop the iron from making it out to the ocean. And then we see them again at the end of the Proterozoic, associated with these banded iron formations and ice ages, okay? And this is the time when the Earth is thought to have frozen over. The whole snowball Earth hypothesis is going on at this time. And it's highly integrated in lots of ideas, and it's basically burying carbon in vast amounts, raising the oxygen levels a lot, okay, to about 10% of levels today. And this reaction that's going on between climate and oxygen, all of that, set the stage now for us to move out of the Proterozoic and into the Phanerozoic. There's enough oxygen now that you can have big organisms, not just single-celled, but multi-celled organisms. Multi-celled organisms with muscles that can move, okay? So these are different ones that are coming at the end of the Proterozoic, and this is the one that defines the very end. It's a trace fossil, which is showing that you've got something with muscles that can move and dig through the sediment, okay? And then we come into the Cambrian when we have fossils. And I need to stop there. Thank you.